Optimization problems. These are the types of problems we're going to look to maximize revenue, minimize costs, maximize profit, those sorts of things. So our strategy that we're going to use for solving these sort of max-min problems are first, always read the problem carefully. If relevant, make a drawing. Make a list of appropriate variables and constants, noting what varies, what stays fixed, what units are being used. If you made a drawing, label the measurements. Step 3, translate the problem to an equation involving a quantity to be maximized or minimized. Try to represent Q in terms of the variables of step 2. Finally, in order to maximize or minimize, we're going to need our Q, our quantity, to be a function of one variable. So we may have to use one equation and solve it for one of the variables and do a substitution. And then once we do that, once we have a function of one variable, we can use our strategies for finding a maximum or minimum of a function that we learned in using the first derivative test and the second derivative test. Okay, so let's tackle a few problems. Maximizing profit. We have Riverside Appliances, and they're making new refrigerators, and they're marketing them, and they need to sell X refrigerators, and they're going to set their price based on selling that number of refrigerators, and they also have a cost function. It determines that the total cost of producing is given by the function there, 5,000 plus 0.6x squared. So we have a couple different parts here. First is to find the total revenue. So revenue, revenue is, if we don't have a revenue function, how do we calculate, how do we find a revenue function? Well, if I'm selling cans of soup and I want to see how much money I'm making from the cans of soup, I'm going to take the number of cans of soup and multiply it by the price that I'm selling the cans of soup at. So if I'm selling them for 50 cents and I sold 10 of them, so 10 times 50 cents would be $5. If I was selling them for 20 cents and I sold 10 of them, I would make 10 times 20 cents or $2, etc. So it's no different here. So our revenue function is going to be X times the quantity, 280 minus 0.4x, or 280x minus 0.4x squared. This is our revenue function. Now this is not what we are maximizing, but it is a step in the process. So that was part A. Part B is to find the profit. Well, what is the relationship between profit, revenue, and cost? Profit is revenue minus cost. So our profit function, which we just calculated, was 280x minus 0.4x squared minus our revenue function, minus our cost function. So minus 5,000 plus 0.6x squared. And so that would give us, let's see, so 280x minus 0.4 minus 0.6 is minus 1x squared, and then minus 5,000. This is our profit function. Now, part C, if we're following along our strategy, is now we've gotten our function Q that we are going to maximize. We already are in a function of one variable, so there's nothing else I need to do, and I just need to find the maximum. So in this case, I have a quadratic, and the quick, easy way here is to find a derivative. So part C is how many refrigerators must I produce and sell in order to maximize profit. So if I find the derivative, that's going to be 280 minus 2x, and I set that equal to 0. I find that x would have to be 140, and I'm going to do a quick second derivative test, which is negative 2, which tells me concave down, which means the only place I have a derivative which is equal to 0 would yield a maximum. So I would need to sell 140 refrigerators to maximize profit. And part D says what price? Well, we have a relationship between price and number of refrigerators, and that is that P equals 280 minus 0.4x. So when x is 140, P is 280 minus 0.4 times 140, which is Getting out our calculators. 40, and then 280 minus that. 224. So we would set our price at $224 in order to maximize. So notice the difficulty it really here is sort of putting together the pieces in order to find our profit function. So the first thing we needed to do was to calculate our revenue function using revenue is number of items times the price you sold them at. Then I had to be careful in calculating my profit function that I was subtracting off every term of the cost function to get my profit function. And then from there, I'm just using the skills that we learned in the first and second derivative test. Take the first derivative, find the critical value. That's the place where we have a horizontal tangent. Do the second derivative test to notice we're always concave down, which makes sense. This was a parabola. So therefore, where we have a horizontal tangent, that can only occur at a maximum. And so that tells us how many refrigerators we need to sell in order to maximize our profits. One thing is you always want to verify that this is in fact a maximum. So we used the second derivative test to verify a maximum. You can't just stop at, oh, x equals 140 and we're done. You have to verify that you have a maximum. And then from there it was just a plug and chug to answer part D. So let's take a look at another one. All right, now this is a little bit more complicated because it's not just a matter of, oh, here's your price function and revenue is just the number of items times your price. We have a couple other things to take into consideration. So Edwards University wants to determine what price to charge for tickets to football games. At a price of $18 per ticket, attendance averages 40,000 people per game. So when P equals $18, attendance is 40,000. And every decrease of $3 to the ticket price adds 10 people to the average attendance. Now we have to be careful here because we want to do this if per dollar, not every $3. So this says that if I decrease to $17, my attendance is 40,000 minus 10,000 over 3, right? So basically for every dollar, my attendance drops. So we just want to keep that in mind. All right, now, and it says every person at a game spends an average of $4.50 on concessions. What price per ticket should be charged to maximize revenue and how many people will attend at that price? All right, so we've got two different things going here in our revenue. So let's try and write that out before we even start to put on any formulas or anything like that. So revenue is two parts, right? Revenue from ticket sales plus revenue from concessions. All right, well, revenue from tickets is, excuse me, the number of tickets I sell at a particular price. And I know that when I charge $18, attendance is 40,000, and for every $3 I lower the price, the average actually goes up. If I gotta make an adjustment back up here, 40,000 plus 10,000 divided by 3. So how many of these $1 decreases do I want to incorporate? So this is a matter of my price, which is 18 minus X, so how many $1 decreases, times my attendance. So my attendance is 40,000 minus 10,000 divided by 3 times X. So times these number of $1 decrease in increments. So this is my price per ticket, and this is my number of tickets. Then my revenue from concessions is going to be each person is spending $4.50, so the total amount I'm raising from concessions per person, times the number of people. And again, I'm going to use that 40,000, gosh darn it, I keep screwing that up, plus 10,000 divided by 3 times X, right? Okay, so now we've got a revenue function. So I'm going to do a little bit of algebra here. So I'm going to have you pause, do a little distribution, and come back and come up with a revenue function that will be a polynomial. So you're going to distribute the 18, then you're going to distribute the x, etc. Then you're going to distribute the 4.5 and collect your like terms and then come back. Okay. All right, so go ahead, pause, and do your algebra, and then come back. We'll compare our answers. Okay, so after we've done some algebra and collected our like terms, so a little bit of the distributive property and then collected our like terms, we get a revenue function of 900,000 plus 35,000x minus 10,000 over 3x squared. And again, now this is the quantity that we want to maximize, right? This is our quantity we want to find the maximum of. And so we're going to do the derivative, find the derivative, which is going to be 35,000 minus 20,000 divided by 3x. And we set that equal to 0 and solve. And so that would mean, let's see, what do we get here? 70,000, 35,000 equals 20,000 divided by 3x. So 35,123 times 3 and divided by 20,000 is 525. So we would reduce the price by $5.25. We want to verify this is a maximum. So our second derivative would in fact be negative 20,000 divided by 3, which is negative, which tells me concave down, which tells me a maximum. And how many people will attend at that price? Well, we're going to plug that into 40,000 plus 10,000 divided by 3 times 5.25. So let's see what we get. 5.25 times 10,000 and divide that by 3 and add 40,000. 57,500 in attendance. Okay. So the price per ticket is, this is our reduction, the $5.25. So 18 minus 5.25 would be $12.75 at $12.75. So that would be our attendance, and that would be the ticket price we would want to set it at. Okay. So notice we had to break it down here in terms of like revenue from tickets plus revenue from concessions, and we needed to also determine that we had to do like a per dollar change, and so we had to use the 10,000 divided by 3 here, so that we made sure that we're calculating each a small increment of change. So for every $1 in decrease in price would have a particular effect on attendance, rather than the $3 at a time. It wouldn't come out quite right if you did that. And then the rest of it is, you know, it was algebra and a quick derivative and doing our work there. So you just have to make sure that you're coming up with the right function that you're going to maximize, and that you verify that you in fact have a maximum.